Hello, everyone, and welcome back. Today, in this video, we want to see a little bit about the two important issues that we need to fix when we are working with a deep neural network. We will classify these issues as vanishing and exploding gradient problem. Let's see what these problems are. As we discussed before, the backpropagation algorithm works by going from the output layer to the input layer, propagating the error gradients on the way. It means that, as we explained about backpropagation, when you want to train a neural network, you need to go for backward and forward through the network several times. And every time that you are going backward, it means that you are evaluating the errors. These errors that we are evaluating are considered as the gradient or the derivative of the loss function. Once the algorithm has computed the gradient of the cost, please remember that when we are talking about gradient in this text, always it means that we are talking about derivative. The derivative and gradient have the same meaning. When the algorithm has computed the gradient or the derivative of cost function with regard to each parameter in the network, it uses these gradients to update each parameter with gradient descent step. Because as we explain in gradient descent, when you want to use gradient descent, it means that every time that you want to update a parameter, the derivative of the loss function with respect to that parameter should be considered for updating the weight or every parameter, bias and weights. Then the issue can occur here is the case that the gradients that you are evaluating are too small. If you have gradients which are too small, it means that the weights that you are updating won't be updated, or they will be updated very small. So then when this happens, it means that if gradients often gets smaller and smaller as the algorithm progresses down to the lower layer, then it is possible that in the gradient descent step, your parameter won't be updated. And if your parameter won't be updated, it means that your algorithm won't converge. It means your algorithm won't give you a good solution. So this issue is called vanishing gradient problem. When we say that then vanishing gradient problem means that the the weights won't be updated because the gradient of the loss function with respect to that weight won't change. And if it will not change, it means that your parameter won't be updated. Then the same issue can happen in the opposite direction. Opposite of the vanishing gradient problem is happen when the gradients gets bigger and bigger. It means that every time that you go backward and forward through the network, when you evaluate the derivative of the loss function with respect to each parameter, you can see that these derivatives are getting bigger and bigger. When something like this happen, again, when you want to update your parameter in the gradient descent step, your parameter will approach infinity. And when something like this happen again, it shows that your parameter won't converge to anything. And this issue is called exploding gradient problem. This problem mostly occur in the recurrent neural network. We do not talk about recurrent neural network in this class. This is mostly deep learning topic. But for some of you who are interested, I can say that recurrent neural network is one neural network which is mostly used in NLP tasks. Okay, more generally, deep neural networks suffer from unstable gradients. Different layers may learn at widely different speeds. Although these unfortunate behavior have been observed for quite a while, it means that we have seen this issue from the beginning of neural network in 60s. And people could see that this issue can happen if the number of hidden layer is too much. But until 2010, we could not find any progress to fix this issue. We want to see a little bit about the progress that we reached in 2010. In 2010, very important paper was published by two giant names in the field, Joshua Benjo and Xavier Gorort. And something that they did included the combination of the popular logistic sigmoid activation function and weight initialization technique. In 2010, the most popular method to choose weight was random initializing using random distribution with a mean of 0 and a standard deviation of 1. Why this is important, as we explained before, when we want to run backpropagation, we should start by initializing the weights, because as we explained before, through the training of the network, when we do backpropagation, we should start by initializing the weight. And when we go toward the network, in every time that we run the gradient descent or any other method, we will update our parameters. That means those initial values that we consider will be updated through the process of training. Until 2010, when people wanted to randomly choose initial values for parameter, they choose these values from the normal distribution of mean 0 and a standard deviation of 1. This kind of normal distribution usually is called a standard normal distribution. And it is very popular method actually in statistics. It means that one very popular distribution that we have in statistics that people work with a lot is normal distribution. Then when people wanted to choose initial values for parameter, they choose those initial values from a standard normal distribution. Something that Joshua Benjo and Xavier Gollert found out was that maybe in order to prevent from reaching to exploding or vanishing gradient, maybe we need to choose initial values for parameters in a more interesting way. In short, they showed that with this activation function, means with sigmoid function, and this initial scheme, the variance of the output of each layer is much greater than the variance of its input. Something that they showed was that if you use sigmoid as the activation, and if you choose your initial values for parameter from the normal distribution, then you can see that the variance of the input layer and the variance of input to each layer is much bigger than the variance of the output. It means that when you send some parameters to one layer, then you can see that the variance of output is much bigger than the variance of input. And when we go forward to the network, the variance keep increasing. It means that in the first layer, for example, we can see that the variance gets, in the first layer, we can see that after passing one layer, we can see that the variance gets bigger. When we go to the next layer, again, variance gets bigger. When we go to the third layer, the variance gets bigger. Therefore, when you have lots of layers, you can see that they could see that when you have lots of layers, variance gets bigger and bigger and bigger. And they noticed that it may cause the issue. This is actually made worse by the fact that the logistic function has the mean of 0.5, not 0. So then in order to fix this issue, Gollert and he and other researchers, giant names in the field, in their paper propose when using the logistic activation function, means when we use sigmoid, the connection weights of each layer must be initialized randomly as follows. We can use normal distribution with mean 0 and variance of 1 over fan of average, when fan of average can be evaluated by this formula. Fan of average means that the fan of input plus fan of output divided by 2. when the number of inputs of the neurons are numbers are called the fan in and fan out of the layer. It means that when you consider when you consider input of a layer and output of the layer, we will evaluate the number of the number of neurons, and these number of neurons for inputs give us fan of in. And when we consider the number of layers in the output is considered of fan of out. So then they consider that if we use the initial values for weights from the normal distribution of mean zero, but variance which can be found by using this formula, or if we use uniform distribution between negative r and r, when r can be found by using this formula, radical square root of 3 over fan of average, again when fan of average can be found by using this formula, then we can fix the issue of increasing the variance for each layer. This initialization strategy is called Xavier initialization or Colbert initialization. We will explain in another video that how by using Python, these initialization can be used. Again, as you can see, we are using some math here, but we will explain in another video that these initialization value can be found very easily when we are using Python. So I think it is a good time to stop. Thank you.